So I'm a little late in posting the second half of week nine's videos. All that's really left, however, is the last three examples that are shown in the book. We're looking at the first one here that's on page 228. And what's nice about this is that the authors give us the answers. And of course, it makes things easier for future problems if we can learn how to plug them in to Excel. So in this example here, we're seeing that there's a power plant with 111 incandescent light fixtures that are on 24 hours a day, 7 days a week, year round. These lamps were replaced with compact fluorescent lamps, which saved over 70% of the energy and last 10 times longer. Because the lamp life is so much longer, there's a maintenance relamping labor savings. So that's what we're going to try and solve. All right. So again, they put all the data in here for the plant, 111 fixtures every hour of the year. The cost for electricity use is 5 cents a kilowatt hour. The demand charge is $120 per kilowatt per year, or $10 a month would be another way to look at it. They're paying their maintenance guys $20 an hour. That would be the people that are actually changing these lamps out. And by calculating the amount of time it takes to do this and dividing it into the labor rate of $20 an hour, we see that for 5 minutes of labor, that's $1.70 a lamp. We also learn that it's not as simple as just screwing in the light bulb, right? There might be a baluster and there may be something else that needs to be replaced. So we have to buy this $15 fixture. So what's next then is that we'll look at the existing data. So for X number of years, they've been running all 111 of these lamps. We can see the lamp style and type here, but most important, we see that it's 150 watts, and they're paying $1.93 a piece for them. The length of time each one lasts is 750 hours. So if you think about it, if these things are on 7 days a week, 52 weeks a year, 24 hours a day, then they're going to be changing these lamps quite frequently. So someone came up with an idea of putting in a new T9 type, which only uses 30 watts. However, the cost of the CFL and the ballast and the lamp and the socket extender is going to be $30. Eventually, we'll only have to replace the lamps, and those lamps at the time of this posting were $10 a piece. And the good news is these lamps are going to last 10,000 hours, so well over a year. So the calculations that are shown here are pretty clear, and our job then is to put that into the Excel spreadsheet. So let's go over the Excel spreadsheet right here, and you'll see that I put all the data in here. Here's the number of fixtures, here's the number of hours, here's the kilowatt, the cost, demand charge per year, cost per kilowatt hour, labor cost, maintenance. So these are all the things that were in the book. I did add this last cell here, which gives us the multiplier to convert watts into kilowatts. And then the next data that we need is the existing, right? So the existing lamps are 150 watts, which costs $1.93 each and only last 750 hours. The new lamps only use 30 watts. However, it's going to cost us $30 to refit them. And the lamp itself, each time it needs to be replaced, is $10, and there's the life, 10,000. So the calculations we're going to need, and again, we're just following the book here, watts saved per fixture, right? So if I click here, it's going to show me that we're going to subtract, right? So if I clicked in the cell, this is the data that I plugged in. I did equals D3 minus D7, right? So we can see D3 is this cell here, the 150, minus D7, which is 30, and of course we get our answer, 120 watts. So that 120 watts is going to be saved. Well, how much is it going to be saved? Well, so the demand savings in kilowatts, we will take, again, if I look at the cell here, I can see the formula that I put in here, and I put in, it says B2, 111 fixtures, times F2, 120 watts I save by using the more efficient lamps, times B9, turning watts into kilowatts. That's what we're doing here. So again, the cells all show up for us. You can slow this video down or pause it if you'd like, so you can do this work yourself. And perhaps some of you have a more elegant solution for this than mine. It's quite possible. Some of you guys do this, are doing a really good job on this. So now in order to solve for the kilowatt hour savings, we have to multiply the number of what that demand is, the 1332 right here in F3, and we multiply that times the 8760, the number of hours in a year, right? So 13.32 kilowatts times 8,760 hours, and that gives us the 116,683.2 kilowatt hour savings, right? Now is where the math starts getting fun, because we're going to next calculate the lamp replacement cost. Okay, so the lamp replacement cost, you can see it's a pretty significant formula that we've got here with lots of parentheses that are easy to forget and not have enough matching ones. You'll notice that there are colors coordinating the different cells, and there's colors coordinating the different parentheses. So in this one here, we are going to take first we take B2, the 111 fixtures. We're going to multiply that times D9, right? D9, which is the $10 we pay for a lamp. And we multiply that times the quotient of dividing the 8760 hours by the 10,000 hours, right? And so that number is going to be used to as the base, and we will subtract from it the same type of number. Right here, we're going to take B2, 111, times D4. In this case, the $1.93, how much those cost, but we have to multiply that times the frequency we replace those lamps, which is again the B3, in this case, divided by 750, right? And so the lamp replacement costs, wow, we're going to go in the hole. It's actually going to cost us more to replace these lamps, right? So we have a negative number here. 1,529.85. So that, notice it shows up as a negative number. All right. Actually, so it shows that we're actually saving money. It's going to cost us $1,500 less per year to replace these bulbs, even though they cost $10 more than the others. All right. So now the relamping. Now here's our labor savings, right? The labor savings show up in this block here. And so the labor savings, again, we're going to use the B2, the number of fixtures, and we're going to divide that by B7, the cost of or multiply that times the cost of the labor. And that labor then gets multiplied times the ratio, right? So we're going to take the 8760 divided by D5, right? The 750 hours. And from that, we subtract the 8760 hours divided by the 10,000 hours. And we're going to see that we're going to be saving $2,000, $2,038.71. Now, notice the examples that I'm showing here, I've got it shown up in dollars and cents, which did not round. Okay, so it didn't round the numbers here compared to what we've got over here. Right, here's these same numbers. Right, so here's our negative. So we got $2,039, right? And what did we get over here? Over here we got $2,038. So again, I'm just pointing out how rounding errors, our answers might be a little bit different because of the way we round. All right, so the maintenance relamping cost shows up here, right? Maintenance relamping costs, again, this is the total savings, actually the total annual dollar savings. So we have to multiply the F4, right? This is the number of kilowatts we save. So we have to multiply the number of kilowatts we save in F4 times the 5 cents per kilowatt hour. And to that, we have to add the demand charge savings, right? So the $13.32, or the 13.32 kilowatts demand, we multiply that times the 120. This 100. Oh, I picked the wrong 120. It's going to come out the same because they happen to be the same number. But notice I selected F2 here instead of B4. So where's the F2? Let's get rid of that. Get rid of that. And we'll say this one instead. B4 times F3. And from that we have to subtract this negative cost. Okay, I said that wrong a moment before. It actually costs us more money. So we lose a little money on these $10 a lamp. and then the money we save on the maintenance. Okay, now what I'd like to point out here though is that this negative number, I don't know if you remember when compact fluorescents first came out, they were pretty expensive. The cost came down dramatically. So although in the first year of this scenario, they may have been $10 a bulb, but by the second, third, fourth, and fifth, all the way up to the 10th year, I think we would find that those lamps would be a lot cheaper. And so we would be able to recalculate this and see we'd be saving a lot more money. Now the implementation cost shows up here as B2, the 111 lamps. Whoops. Okay. And we have to multiply that times the B8, right? My labor cost. Oops, spelled labor wrong. Let's fix that. Oops, cancel that. Got to fix labor cost. Low bore. That's not good. Labor cost. So again, we take the B2, right? The 111 lamps times the 15. We're going to multiply that times the sum of the refit labor plus the cost for the refit, the parts, right? All right, so that's times 45 total. And so again, we can see the answer just like in the book, $1,445, right? $4,995. Where did that number come from? All right. And then finally, then, what we have to solve is our simple payback. Our simple payback, SPP, simple payback period. The book shows 0.5, and again, if I come over here and I use my rounding, it rounds to 0.5. So it's actually less than a half a year. So we're really doing well on this one. This is a pretty good no-brainer. Less maintenance needed, and we're going to save money. In the first half year, we're saving money. All right. Let's see, we've got to go to the next one. And the next one begins after talking and learning about ballasts. We're going to then look at example 5-6 on page 332. And this here, we've got the prisoner holding cell in the courthouse that utilizes two fixtures that have two F40T12 lamps to illuminate an 8x12 area. The cells are usually occupied a maximum of 45 minutes per day, and they are illuminated 12 hours per day. Now, the way we read this, it makes it sound like somebody comes in and in less than an hour they're gone. Well, it may actually work out differently than this. It could be that that 45 minutes a day is spread out over the whole day. What if it's only 15 minutes 3 times? So we don't know, but we're just going to go with the numbers that they gave us. So, currently the cells have been illuminated 12 hours a day. How much money can we save by installing occupancy sensors in the cell? We have to calculate the simple payback period and the return on investment if the sensor cost is $70 and that they have a 10-year life. The electricity costs are 8 cents per kilowatt hour. So in our solution, they're going to get some assumptions that maybe we didn't know about. And so what they're saying is that the occupancy sensor has a delay built into its operation. So what that probably means is as soon as somebody walks in, the lights turn on, and even though they're only in there for 45 minutes, the delay will keep them on for yet another hour a day. All right, so, another 15 minutes rather, to give us a total of 1 hour a day, 5 days a week, 50 weeks a year. Further assumptions include that each light fixture and its ballast, with its ballast, so that's ballast included, is going to use 80 watts for the 2 lamps plus an additional 15% for the ballast. All right, so 12 watts. So this is how we're coming up with the numbers. And they show us the figures here, and it looks pretty simple. If we just use a calculator, we can crank this out really easily until we get down to this ROR, which is also known as the internal rate of return. So return on, so ROR and IIR are both the same. So let's go look back at the Excel spreadsheet now. And so again, this is the whole thing. And I just copied and pasted it in here, and I've highlighted and bolded the areas that are important to us. All right, so 1, how much can we save by installing the occupancy sensors in these cells? How much can we save? Okay, well, we save $40.48. And how are we doing that math? Well, if I click on the cost savings, right, so first I had to put all the data in that each cell has 2 fixtures. There's 2 lamps in each fixture. Each lamp is 40 watts. The ballast is notice how I actually had Excel do the math for me. I had it multiply the 40 times the 2 times 15%. That's how we came up with the 12. And then we added them all together. All right, so there's the 92 watts per fixture. How many hours a day are there going to be used total? 1 hour per day, right? And remember up here it told us 12 watts or 12 hours a day, right? So by only using them on, by having the timer only keep these on for 1 hour a day, we're saving 11 hours a day. So that's important to figure out how much we're actually saving. There's our 5 days a week, 50 weeks a year, 8 cents a kilowatt hour. And again, I put this 1,000 watts per kilowatt multiplier in here because we're going to need it. All right, so again, the first question is how much do we save? So again, we click here in the cost savings, and I entered in the same data that we saw in our example, right? It gave us the answer right here, 2 times 92 times 0.001 times 11 times 5 times 50 times 0.08. Wow, that's a lot. So let's see how I plugged it in. So I plugged it in E2, right? So here's my E2, there's my 2, times E6, the 92 watts, times E13, which is the turning the watts into kilowatts, times E8, which is the 11 hours a day that we save, times E9, 5 days a week, times E10, 50 weeks a year. All of that gets multiplied together. And from that, then we multiply all of that times the 8 cents per kilowatt hour. So it's kind of important to see how I put the parentheses together to come up with the $40.48. So that's what we saved. All right. So that was question number 1. Question number 2, calculate the simple payback period and the return on investment if, where'd it go? The sensors cost $70 installed and have a 10-year life. All right, so right here, there's our $70. So SPP is going to be equal to the timer cost installed, $70, divided by the cost savings, the $40.48. Notice I come up with a negative 1.73 because I made this negative here. I did that in order to make some of these other things we see here work out. Now, I'm going to use this example to help explain some stuff from chapter 4. And we were messing around with the value of money over time. So we've got the SPP. That was one of the things that they wanted. And we need to now come up with the return, the rate of return. That was the ROR, right? We want the return on investment. I got some problems with the way the authors are not sticking with one term. So they're in this question, they're asking for the return on investment rather than the IRR, internal rate of return, or the ROR, rate of return. They all mean the same thing, but they keep jockeying them around either way. So at any rate, so here's our IRR. And I did this a couple ways here. Now remember in the example, right? Let's go back to this example. Right, so we got the 1.73 years, right? And so what we have to do then is we have to use this 10-year number here, right? We have to use this 10-year number, and we have to use this $40.48 to come up with how, whatever that multiplier is going to be over 10 years, how we're going to get, what do we divide 70 by to come up with $40.48. All right, so it's kind of strange how we do this. So I grabbed this sheet, this portion of one of the sheets we used back in the last chapter, and notice in this spot here, I have to put the 10 years in, right? This is pretty important, 10 years. This is the 10-year spot right here, and that has to get plugged in here. And then I just started changing this number until this factor value got to equal something close to the negative 1.73. Now I'm going to open this up. I'm going to actually give us a few more decimals here in the 1.73 to show you how we came up with the 57.2, right? So remember in the book, he says 57.2 will do it, right? Well, if I use 57.2, that doesn't get me to 1.73, right? So watch this. So Throughout our examples, we've had internal rates of returns. Our MAR tables, we've typically used numbers like 8% and 10%, right? So if I put 10% in here, whoop, not 19, if I put 10% in here, notice that factor value is 6.1. It would take 6.1 years if we were only getting a 10% return on our money. Well, it's not. We need this number right here to match. This factor number here is supposed to match our simple payback period. All right, so 10 didn't do it. What about 20? So notice as my interest rate goes up, my factor value goes down. The higher the interest rate return I get, the lower the simple payback period becomes. So we'll go to 30%. Okay, so I've made it to 3. Now we'll go to 40%. Ah, cool. Well, now let's go to 50%. So at 50%, notice, whoops, I hit the wrong number. At 50%, we're getting close, 1.96. We'll go to 57%, 1.73. Well, we might be happy and leave it at that, but notice we've got to get that number even lower. So as our interest rate goes up, our factor value goes down. So let's say 57.1 takes us to still 1.73. But remember, when I change my rounding to 4 decimal points, the 1.73 became 1.7292. So now we'll do 57.2. Bingo, look at that, 1.7292, 1.7292. Pretty darn close, we can live with that. All right, so that is our internal rate of return, 57.2%. Okay, and if I come back here and I can increase this, we get the 57.2, because notice I said equals, right? Here in my rate of return, ROR or IRR, right? We've got equals H4, and H4 was part of this table that I showed you from the download. All right, now there's one other thing that I want to show you here before we move on. This is something that was not made clear in any of the instruction, but was made clear in the answers for this particular chapter, or for chapter 4. All right, so do you remember the answers for problems 4? It was page 50 of that, and the bottom of page 50, which was for problem 4.7, the very last line says the MAR that drives the present value to 0 is 20.9%, which is the IRR or the ROR. So I put this table in here, right? There's a formula that we can use to calculate IRR, and that's this one that's shown right up here. IRR is equal to B7, so we start with the cost of the upgrade, negative $70, and we come down to B17, which is all 10 years. So at year 0, we spend the $70. Years 1 through 10, we make $40.48, and based on the rate of return, or the IRR, it's going to show you what the net present value is at the end. And that's part of what we're trying to do here. All right, and so that net present value, notice here's another formula that we didn't talk about in the last chapter. Well, I did in the problems, right? And so this is a way to solve for net present value. And so again, this is what I'm trying to get at here. So this 57.2% that we calculated over here in this other worksheet, that drives the net present value to 0. Watch what happens if I come over here and I change this number to something else. Let's say I'll change it to 33%. So that means at the end of 10 years, the net present value is $45, right? Well, for tax purposes, well, this is what they're getting at here. So nowhere was this explained about driving the present value to 0 by using this IRR number. So I thought it was important for me to show you this. So again, 57.2% drives the net present value to 0. All right, that's 5-7. Wasn't that fun? Let's go back over to here. We'll look at the last one. Example, I'm sorry, that was example 5-6. And in this case, we're going to look at example 5-7. And on 5-7, We're going to learn about the Gator Plastics Company. And because of all their growth, they're going to add on a new production room. So the engineer responsible for selecting the lighting system has some questions. He's got a couple ideas. Well, one alternative uses 40-watt light fixtures and with 34-watt lamps in each fixture and a ballast that drives all 4 lamps, which consumes 20 watts. Costs $2,000 to buy, $2,000 to install. The second alternative is going to use for the same 40 fixtures, same 40 holes in the ceiling tiles, right? But in this case, we're only going to have 3 40-watt light bulbs and 1 ballast that drives all 3 that uses 15 watts. Thing is, there's a $400 cost kicker on this. This costs the same amount of money to install. If they both last 6 years, and the lights are used $2,000 per year at the rate of 8 cents per kilowatt hour, let's determine which would be the right alternatives to select. So we have to calculate the 3 standard economic evaluation measures for each alternative. The simple payback period, the ROR, also known as the IRR, and the benefits to cost ratio. So that's all of this. And so it's all pretty much laid out here for us. And hopefully, after we've seen that last spreadsheet, we'll be able to plug some of the same information in. All right, so as you can guess, over here in this spreadsheet, I plugged in all the information up here so I don't have to keep going back and forth. And here's alternative 1, here's alternative 2. This one has, alternative 1 is 4 lamps that use 34 watts each. Instead of having it do the percentages, I plugged in the 20 watts for the ballast and giving us a total of 156 watts, just like it showed us over here. Total of 156 watts. 40 fixtures times 156 times 2,000 hours. All right, so let's come back and look. So again, here's all the data that we need. All right, here's my 8 cents per kilowatt hour. Here's my 2,000 hours annually, and here's my watts to kilowatts multiplier. So this is how we came up to 156, right? So we took B4 times B5, right? B4 times B5 plus B6 gives me 156 watts. Do the same thing over here for the 135 watt. We're going to take the 40 watts times 3 plus 15, there's 135. So we can see we're saving a little bit here. And so when we do the math, we're going to multiply all the things together. So we're going to take B3, the number of fixtures, 40, right? So we're going to take the 40 fixtures times the total watts, 156, times E3, the rate, 8 cents a kilowatt hour, 2,000 hours per year, and converted all the kilowatts, right? And so again, we come up with $998.40. That's the cost to run this alternative. If we go with the unit, with the 3-lamp unit, doing the same kind of math, right? We did the same thing up here, right? We're going to come up with $864. So we're going to save $134.40 every single year. And notice we put in the number of years here is 6 years, right? And so now the first thing we need to know is, all right, so here's the purchase cost. They're both there's $2,000 to buy alternative 1, $2,400 to buy alternative 2, $2,000 to install either one, so that's a wash. And when we subtract the $2,000 for A1 from the $2,400 of A2, we can see that the cost premium is $400. We're going to need that number so that we can calculate what the simple payback period is down here. That simple payback period will be calculated by dividing the purchase cost, $400, by the annual extra savings, $134.40, and notice it's about 2.97 years. What does the book say? The book says pretty close to 3 years. Well, if I just use 3 years, these other numbers that they show me aren't going to come out that way. All right, so next we have to calculate the cost-benefits ratio, right? And so the cost-benefits ratio is shown here, and we are going to have D8, right? So D8, right here is the 134.40, excuse me, the 134.40 times G16, right? G16 is this factor down here. This is this factor down here, right? And we're going to divide all of that by D9 in order to come up with this. So how did we do that? Well, I remember when we had to get that information here, we had to use the 8%. Whoop, let me get out of that. We had to use the 8% and the 6 years, right? Right? And that's where we ended up with this value here, the 4.46. Okay, so that's my factor that I have to use there. All right. All right, so that's where we come up with the 1.55, just as shown in here, right? Okay, so the present worth, again, we have to use that same table here. How do we come up with 24.3, right? The 24.3, again, I'm trying to get to 3% here, right? I'm trying to get to, he wants me to do 3%, right? If we look at 3% over here, he says 3 years. He wants me to get this 3-year period. That's what this number has to be. So when he calculated that it was 24.6%, I kind of get a different number here. I get 24.3 is going to get me to 3, right? But what if I actually go up to, let's see, we want that number a little lower. So if I say 24.5, that brings me to 2.97, 24.525. Still not there. 24.55, 24.6. Look at that, 24.6 is getting me a lot closer to what my actual was. So because he rounded over here to 3 years, his ROR is actually not going to work out the same, right? So when we do these calculations, we have to be a bit more exact. So I've used a tool that we used from chapter 4. And again, that's the idea. We want to be able to take these tools that we've used and bring this to our next jobs and get us a good job so we can help companies to come up with good EMO strategies. So that is the end of the week 9 videos. Most of you guys probably figured this out without my help, but here it is anyhow. I'll get this posted, and you guys can work on your assignments.